I'm going to go ahead and start my talk now. My name is Kyle Kastner. I work at Southwest Research Institute as an engineer. I'm also a student at University of Texas San Antonio. And my talk today is about trends in deep learning. A lot of you guys have probably heard deep learning. It's kind of the new hot thing in machine learning research. So hopefully I can enlighten you guys a little bit more about what that is and what that means and how you can use it and frameworks in Python for doing deep learning. So, just like the talk before me, I'm going to spend a second on the W's, specifically who, what, when, why, and where. So who, that's an introduction for me, just did that. The what. Deep learning is currently being used for object detection in unlabeled images, document tagging, speech-to-text, speech recognition, generative modeling, and a whole bunch of other interesting applications. So the reason this has become really hot is because researchers in each of these areas have taken deep learning, applied it, and basically decimated outstanding research. So machine learning researchers spend a lot of time and effort sitting down, looking at their data, and hand coding features for different stuff. If you're looking at images, people spend a lot of time trying to make feature extractors that can find unique things in an image that might be indicative of something special. Things like corners or circles or curves, things like that. If you're looking at speech, there's things called phonemes that are basically the building blocks for words and phrases. For words, like in text, there's parts of speech and nouns and verbs and grammar, and that changes based on your language. But deep learning is kind of above all that. The goal of deep learning is to input data, spend a long time and compute power churning on that data, and at the end learn representations of what you think the data means and use that directly. So the goal of deep learning eventually is to basically take humans out of the loop, feed a bunch of data, spend computer power so humans don't have to waste their time. The when, research in deep learning really started back in 1957. There was an algorithm called the perceptron. For you guys that are interested in machine learning, that's kind of where everything started. Neural networks and perceptrons and pretty much any algorithm in machine learning becomes hot. Someone publishes a paper that says this is completely unfeasible. Research dies out for like a decade. Deep learning is no different. It's really just an extension of neural networks for you guys that have studied those kind of things. Neural networks kind of went dormant for a decade. The support vector machine became really popular and really useful. And it's pretty black box, so people could just throw it at their data. But deep learning has kind of come back and surpassed the support vector machine. So it's kind of the new hot research, and Google and Microsoft and Amazon and a lot of other companies that are big into processing and big into computing are also behind this. The where, specifically where in Python. So there's a lot of different frameworks and libraries in Python for doing machine learning and for doing specifically neural networks and deep learning. I'll provide links at the end of my slide, but some of these are PyLearn 2, theanets, sklearn. A lot of these libraries, if they use GPU computing, are built on a library called Theano for doing GPU processing in Python. For you guys that look at high performance code, definitely look into that. It's very cool. The why, hopefully I described that a little bit.
Sorry, do you have any that just run on regular processors?
Yes, so Theano also runs just on CPUs. So there's kind of two schools of thought. Me personally, I run a lot of my code on the GPU because I can't afford a server farm. People like Google tend to just do distributed processing, lots and lots and lots of CPUs. And the Python tools support both very, very well. There's another tool called joblib that's very efficient for distributed processing. IPython, which was mentioned in the last talk, also has distributed computing mechanisms. So that's a little bit of the why. I'm going to go over some more. I specifically wrote some examples in Python that I'll provide a link on my GitHub to get to, and you can see those and use them. If I can turn off the caps lock here. Okay, next slide. So the anatomy of a neural network. The building block of everything is a neuron or an activation function. So what I've shown here is 3 different possible activation functions. Top left, you'll see the sigmoid. Top right, you'll see the hyperbolic tangent, or tanh. In the bottom left, you'll see the rectified linear unit. If you look at the literature, or if you're reading press releases or whatever, you might see some of these terms. Basically, what's happening is you have this little tiny neuron. The idea is actually inspired by biology. But you take an input vector, you apply this function to each individual input, sum it together, and send it out as a value. And that's a neuron, by and large. And different researchers have different theories about what happens in the brain. Some people try to map this back to computing. Some people don't. Some people just say, hey, what are the results, and how does this work? So, larger structure. This is the anatomy of a neural network. So a big group of these neurons. The input layer on the left is called the L1 layer in this particular diagram. You'll see another layer next to it that's sometimes referred to as the hidden layer. There can be multiple hidden layers. And then the last layer is called the output layer. Sometimes you also hear about bias units. Really, it's just a neuron that instead of having a value associated with it, it's a constant multiplied by a weighting factor. It's useful for certain types of problems. This particular diagram is called a 636 autoencoder. Excuse me. All an autoencoder really tries to do is take an input and learn a representation of the input that has less features. So basically, you could think of it as a machine way to try to take groups of pixels or groups of words or groups of things that when used in common are identifying for a particular piece of data. Another important point here is that deep is ill-defined. Deep, I mean, is this network deep? Most people would say no. I would say no. But if you have 2, 3, 4, 5, 6 hidden layers, at what point does it become a deep network? It's kind of arbitrary, and right now, if it's anything approaching deep, it will be called deep because people are very interested, and it's a good way to pique interest.
Why are you sending +1 from layer 1?
So +1 from layer 1 for the bias unit is to accommodate for like in engineering terms, like a DC offset. So basically, if you had some data that had a constant offset of 10, that bias unit will let you basically compensate for that 10 automatically. So if you had like 10, 11, 12, 13, the bias unit would take care of that constant 10 offset, and you would learn the 1 and the 2 and the 3. And this is a lot, I know, but the goal of this is to kind of introduce some terms, hopefully get you interested. You can reference these slides, read literature, and hopefully have some idea of what's going on. So anatomy continued. To actually use these networks, at a high level, what's happening is you can have some input, in this case, a handwritten digit. I'll reference a data set called the MNIST digits a lot. That's kind of the canonical data set for testing and showing results. Basically, you can take that image, flatten it out. So in this case, that image is 28 by 28. So you have 784 input values. Feed that to the first layer, apply your functions, go to the next layer, apply your functions, and then look at the error. So if you're trying to classify, did it recognize that this was a 4 or not? If you're trying to do something else, what is the mean squared error? So for every pixel, how wrong were you? Take that value and also the derivative of that value and feed it back through the network, and that's how you update. And the goal is kind of, you can think of it in a physical sense as standing on top of a hill. If your error is the hill, you're at the top, you say, okay, this hill is 1,000 feet tall, but it's the steepest that way. So if I want to minimize my error, I'm going to go along the steepest path. So that's a lot of anatomy. I'll go over a few more terms. I'm going to talk about overfitting. So overfitting is when you have a machine learning function and you've trained it on a whole bunch of training data, and you say, oh man, I've got 100% classification. I am perfect. I am amazing. And then you feed it live data from the system, and it just does terribly. It's worse than guessing, or about as good as guessing randomly. In that case, you've overfit. You've learned weird specific things about your training data, that don't actually happen in the real world. Hyperparameters, you'll see this a lot in the literature. It took me longer than it should have to figure out what that means. All hyperparameters really are if you have an algorithm, everyone has their little tweaks. So, oh, you multiply by 0.2 or 0.3 or 0.5 or whatever, and it's set beforehand. So a hyperparameter, you can think of it as just a knob that you can turn for a specific algorithm. And a lot of the problems in deep learning right now are there are a lot of knobs, and they're very difficult to tune correctly. So a little bit more terminology, and then we'll talk about some examples. So learning rate is a good example of a hyperparameter. The learning rate, if we take our analogy for standing on top of a hill, a learning rate is how far I step every time and take another measurement. If I'm trying to walk down the hill, do I take a small step? Do I take a big step? Do I take a huge step? That's a rate that you pick beforehand a lot of times, and it's very difficult to pick correctly. Dropout is something that's really hot in the literature and in real-world use. Basically, it's a smart way to train a neural network such that it appears like you have thousands of neural networks, and they each have a vote, and your result comes back, and it's like an average of multiple votes. And it's a strong way to make a decision. I won't go into much more detail. If you're interested, definitely read up. You'll see this all over the place. Momentum, once again, this is a lot like physics. If I'm running all the way down a hill, and then the steepest path goes over here, do I change paths immediately, or do I kind of keep going the way I was? Once again, another hyperparameter to tune. So, we have Borat here. He's telling us this is very, very good. Specifically, in my GitHub repository that I'll link to at the end, I have an example of using an autoencoder with standard machine learning tools. So basically, given an input image, run an autoencoder, and then go down to the code layer. So in this case, the input layer is 784 values. We reduce that down to 150 values. You can then take those 150 values, feed them directly into the input of an SVM or a logistic regression or whatever normal machine learning tool you've run across or can find documentation on how to use. And you can see here that versus inputting the raw features, we actually get a minor improvement, but a 2% improvement in classification error, which for no work is pretty thumbs up. I mean, no work at all, let the computer do it, and off you go. This has been done for a long time, and there's some active research in trying to do feature learning, but deep learning is what people are really into right now. So my example 2 in the GitHub repository is a deep classifier. So specifically, it uses a different activation function and different levels of dropout, and most people would say, yes, this is a deep network. It has 4 hidden layers. It ends up having about a 1.8% recognition error. So what that means is the MNIST data set has 60,000 little hand-drawn digits. And the goal is to figure out, is this a 0, is this a 1, is this a 2, is this a 3, so on, all the way through 9. And this is very active research and very useful for stuff like Google specifically is researching a harder version of this. When their Street View cars drive by, they take pictures of street numbers. They take pictures of people's houses. And they want to be able to automatically put street numbers in all of their maps and put people's houses in all of their maps and automatically build their maps. So deep learning is very much one avenue they're doing to take these images and go straight to classified numbers. It's a very hard problem, but I've given an example, and there's a lot of, once again, there's a lot of research on how to do this and do this well. Example 3 is a deep autoencoder. So I won't talk too much about this. It was very difficult to train, very hard to get working correctly, but the idea is very interesting, right? So I've taken these 784 input values, compressed them all the way down to 30 floats, and then recreated the original image. So basically in 4% of the original size, the image on the right is what you get. And this is just based on the input data. There's no, beyond the training parameters, it doesn't really care what your input data is. You could put in whatever. So the interesting idea is if you can get down to a small enough number, one of the main researchers in machine learning coined a term, supermarket search. So if you can take an input and get it down to a very, very small space, you can think of it like a supermarket. If I want to buy oatmeal and I go to the supermarket, I can pull oatmeal off the shelf and I say, oh, what's kind of like oatmeal? Well, I would expect I would expect cereal and maybe bread, things like that. Now imagine that in like a 3D or a higher dimensional space. That's kind of the goal of this. If you can take input data and get a lower dimensional representation that works well, you can start doing searches for things that are similar. So for example, I have a picture of something and there's a necklace in it. This is an example that Google's doing right now on Google+. You can take untagged images in your Google+, type in jewelry or necklace, or they have like 1,000 terms that they allow you to search for. It'll go through your images that have no tags, nothing, and it will give you images that it thinks have necklaces and pets and all this stuff in it. So it's a way to figure out what's in an image from the raw pixels. This is a very active research. The document tagging example I mentioned is a good example of a deep autoencoder. So, in the wild, I mentioned Google Plus image search. This is kind of the most touted delivery of deep learning, and it works pretty well, and Google's definitely behind a lot of the active research in this area. Android speech to text is another area. Microsoft speech translation, if any of you guys saw Microsoft's demo where the guy spoke English and it got converted to Chinese and played back, that was using neural networks to do a lot of the learning. And actually in the last week, Google released a program called Word2Vec. So for you guys that work with text data a lot, Google basically released their deep learning toolbox for taking a whole bunch of words in a document and figuring out what the document actually means. And they open sourced it. It's out there, and I was pretty excited about it. I spent more time working on my slides for you guys. But when I get home, I'm going to be messing around with that. And it's called Word2Vec. Conference-wise, PyTexas, we're now representing some deep learning here. SciPy had a strong contingent of deep learning researchers. PyCon, PyData. There's also the academic conferences that aren't specific to Python, but talk more about the terminology and the complex, nasty stuff I talked about earlier. I'm not even going to go through all the names, but you should be able to Google these acronyms, and there will be conference papers and researchers and tutorials and all that kind of stuff if you guys are interested in learning more. And down below, I just have a spectrogram of voice because I thought it fit in with the speech applications mentioned above. So in the wild, I mentioned some libraries earlier. PyLearn 2 is very actively developed. It's mainly run by the University of Montreal, and they're kind of the forefront of a lot of this machine learning research, along with a few other schools. So they have some really complicated stuff in there. And if you can harness, grad student labor and do useful things in industry, I would highly recommend it. Theanets is a new library. I've been working on that a little bit. It was started by a guy named Leif Johnson, and he's at University of Texas. And for me, I found the library, I thought it was readable and hackable, and it looked cool. So that's an alternative. All my examples are in theanets. That's not really a vote of this one's 100% better than the other. It's mostly a matter of preference. This whole area of the Python ecosystem is very new. So if someone out there is an active researcher, there's a spot for a definitive deep learning library. Scikit-learn is kind of the canonical machine learning library in Python. It's very black box. Here's my data, fit to it, and give me answers. And it works fairly well. It's CPU based, so you can run into limitations with very large data sets, but overall this is a lot of the machine learning in Python. Hyperopt is a new library. I won't talk too much about it, but that hyperparameter optimization that I talked about, the knob twisting, this is a library that attempts to automatically tune those knobs through some research stuff that basically says, pick them at random and run for a while, and if you find the best one, use it. And it tends to work really well. Theano, which I mentioned earlier, is a GPU library for Python. It's got a very interesting architecture behind it. Basically, you define how your computation will work, and then you input numbers and get results. The really nice thing for a lot of mathematics is it does automatic differentiation. So if you do something that needs derivatives, it's not much fun to sit down with a piece of paper and go through your calculus and do the derivatives and hope you got it right and read some papers and, okay, is my derivative okay? Theano takes care of that. It does it automatically. Very nice for certain scientific applications. There are also other libraries that aren't Python. I won't talk about them too much, but I figured they needed a mention on the page as well. So my references, there is an example of a pure Python autoencoder, and the guy that wrote this is contributing it back to sklearn, so that should be usable soon. There's also a big tutorial on deep learning that I linked to that has a lot more information and is very good. It's used as teaching slides for grad school at University of Montreal. And I also used some pictures from some Stanford notes on machine learning. So, as I said before, here's a link to all the slides and examples. If there's any bugs, do an issue, yell at me, I'll try to fix it. And here's a link to theanets if you want to install it. It's also available on pip, so go forth and conquer. Now the floor is open for questions. I know it was a lot, but ask anything.
How much higher math do you need to use it?
So the goal of these libraries is to not need the higher math. If you want to implement new stuff, you do kind of need to know linear algebra and derivatives. It's nothing too wild, but it is math. But to use it, you don't really need any.
Sorry I was late. I mean, so is this just neural networks with more layers?
This is neural networks with more layers, and specifically, oh, sorry, let me repeat the question. Is this just neural networks with more layers? And my answer is yes. The reason that neural networks kind of fell out of favor is that the deep ones were very hard to train, so it was very hard to get answers out. It would blow up to infinity or nans, or you would get junk out. So these researchers spent a lot of time and effort, and in 2006, they found a way to train these deep networks with 4, 5, 6, 7, 10 layers. And that's where the performance came back above the support vector machine, is because they found a way to train these networks that before would just blow up in your face. And so I also saw a question back in the back. So the question was, what kind of academic track do you need to be on to use one of these tool sets? My answer would be to use the tool set very little. You don't actually need an academic background once the algorithm has been set in place. To do it with to do new research and do active development, you typically need a working knowledge of statistics. I mentioned basic derivatives, linear algebra, and then kind of also just a knowledge of what else people are working on. And there's a lot of terminology and a lot of acronyms because most of the documentation is in research papers right now. So there's a big gap for someone that can understand these things and understand them well, to write tutorials, to blog, and to kind of bridge the gap between academia and industry where they keep their stuff kind of private and for just general use. I would encourage all of you to read and learn more about it and contribute wherever you can. I hope the one thing I can get across is you do not need a math background to do this. To use the library, to apply it to new data, you can just go. You can treat it as a black box, and that's the goal of the whole research.
Can you tell me a little bit about your experience, like when you're actually doing
So the question was, can you tell me a little bit about what you've used deep learning for? So the answer is yes, I can, because a lot of the work I've done has been related to either schoolwork or just personal hobby stuff. A lot of the work I've put in recently is contributing back to the theanets library, getting used to it. I started in deep learning 8 months to a year ago. Before that, I was concentrated in other areas of DSP and machine learning. And I've really spent a lot of time, hopefully these examples are a good base point, trying to recreate the existing research that's out there. It's actually really hard. You read a paper and they say, you know, this is the way our neural network looked, and this is the way that we trained it, but they leave out a couple of the little knobs and nothing works, and you say, my network looks the same and I'm using the same data and it doesn't work. So there's definitely a lot of my time has currently been spent on getting up to speed and getting working implementations of this. My eventual goal is to do a lot more research in speech to text and speech recognition. That's kind of where I've come from a DSP perspective. So my time is up. Thank you very much. And if you have any questions for me, feel free to talk to me about it. I love this stuff.